The goal of the Human Biomolecular Atlas Program, or HuBMAP, is to develop a framework for comprehensively mapping the healthy human body at single-cell resolution. Given that each human body is unique, this is an enormous challenge.
In order to integrate data from many individual bodies, HuBMAP will create a common coordinate framework, also called a CCF. A CCF is similar to a postal address system in that it defines the spatial positions of major anatomical structures and cell types within a 3D reference body. This HuBMAP address system is then used to map future tissue samples so they can be explored in their appropriate spatial and semantic context. The CCF must account for human diversity. Here I have 3D printouts of the left and the right kidney of the visible human female. As you can see, the number and shape and size of the individual anatomical structures is rather different, even for one individual.
Diverse methods have been proposed to design a human body atlas. Commonly, reference organs such as this one from the Allen Brain Atlas are designed and used to register new tissue into a 3D Cartesian coordinate system. To create our atlas, we first collect information on key anatomical structures and cell types, along with the biomarkers used to identify these cell types. The resulting anatomical structures and cell types plus biomarkers tables, or ASTC+B, are then used to design 3D reference objects that capture major anatomical structures and the general shape of cells in healthy human adults. Data from the National Library of Medicine's Visible Human project is used to create a 3D reference object library. Cross-sectional cryosection, magnetic resonance imaging, computed tomography, and anatomical images for male and female were used to reconstruct several organs. The 3D nested structure for the kidney is shown here. All objects are named and registered within the HuBMAP Atlas reference system. The CCF can be used to spatially register new tissue blocks. Commonly, the 3D size, position, and rotation of a tissue block is captured by taking photos of the tissue dissection process. However, it is difficult to compute the exact spatial location, rotation, or size of extracted tissue blocks from these photos. The registration software's user interface, or RUI, which is shown here, was designed for usage by experts who collect human tissue and need to document the tissue extraction site. It requires about 5 minutes of training time and 2 minutes for each tissue registration. Currently, the RUI supports gross anatomical tissue registration. Once biomolecular data becomes available, it will be extended to support placement based on biomolecular markers and patterns. The exploration software's user interface, or EUI, makes it possible to explore 2D and 3D tissue samples semantically and spatially across multiple scales. Tissue position data generated by the RUI is used to position tissue blocks. Cell segmentation algorithm results support cell position and cell type exploration. Semantic and spatial search, browsing, filtering, and details on demand are supported. Filters support the selection of sex, age, BMI, etc., making it possible to explore change as the human body grows older or increases in BMI.
The key feature here is we're tying a spatial reference system to an ontological reference system so that we can tie into other things which were also tied to that ontology. Papers, people, cells, research, all kinds of things.
The HuBMAP Atlas and its functionality will evolve over time and become more comprehensive of the many organs and cells that make up our human bodies. Are you interested in contributing to this historic effort to create an open, global atlas of the human body at the cellular level? If so, please contact MCIU, that is, us, to contribute.